In this segment, we're going to look at something called the ideal gas law. Now, it's going to be a little bit different than what we've done with the, kind of some of the individual laws. Obviously, it deals with gases. The word ideal refers to the gases that will obey this law. Gases that behave ideally will follow the pattern here. Now, non-ideal gases we'll talk about later on in the chapter when we talk about the kinetic molecular theory of gases. But for right now, what we want to try to do is relate all four variables together in one equation. And so what we find out is that if we take volume and we look at how it's related to the other variables, we say that, let me look at the relationship first. We say that volume is proportional to the number of moles. It's also proportional to the temperature in Kelvin, and it's inversely proportional to the pressure. And so if we take this and put it into an equation, we get volume is equal to a constant times the number of moles, temperature, and divided by the pressure. Now, since we have all four variables in place here, we can actually come up with a value for this constant. If we use particular units, we can get a value for K. So K ends up being given a special symbol R, and R is equal to the value for R then, if we use the appropriate units of liters for volume, moles for N, Kelvin for temperature, and atmosphere for pressure, is 0.08206. And again, the units then there are going to be liters, atmospheres over K moles. So that would be the value for R. Now the advantage here, and what I'm going to do is I'm going to rearrange this equation now so that it kind of flows a little bit better. If I put the P over on the other side, so I just, again, using a little bit of algebra, multiply each side by P, I have pressure times volume equals N, R, and T. And so you can see that if you were to plug in the value for R, you would have the moles and the K, degrees K, canceling out, and so the units on the right would be liters times atmospheres, which would match up with your pressure times volume on the left. So PV equals nRT is a nice convenient way of remembering this formula. Again, PV equals nRT. And then you just have to remember the value of R. Of course, I'll give you that. You don't have to memorize that, although you should use it quite enough times that you remember it. The advantage here is that as long as you know 3 of the 4 variables, you can solve for the 4th one. So if you have the pressure, the volume, and the temperature, you can figure out how many moles there are, which might be convenient if you're doing a stoichiometry problem. If you know the volume, the number of moles, and the temperature, you can figure out what the pressure would be, and so forth. So what you have there is basically 4 variables. So if you know 3 of them, you can solve for the 4th one. So that's what we'll do in the next problem. And again, the difference we have here is that we don't have a change of condition. We don't have a state 1 and a state 2. All we need to know are those 3 of those 4 variables at one condition, and we can figure out the 4th one. In terms of a problem, then it looks something like this. If we have 4 moles of gas at a pressure of 5.4 atmospheres, and they have a volume of 1,200 or 12,000 milliliters, what is the temperature? So I would take my PV equals nRT formula, and I'm going to solve for the temperature. So I get temperature is equal to, and again in algebra I divide each side by N and R, and so I get pressure times volume divided by N and R, and I know all of these things. I have the number of moles, I have the pressure, and I have the volume. So I can plug in to this equation then, pressure 5.4 atmospheres. And I do want to check as I go along that I have the right units. And so remember R, maybe we should plug that in here just so we can kind of confirm the units there. R is 0.08206 liter atmospheres over K moles. Okay, so atmospheres is the right unit there, so those are going to cancel out for me when I do the math. My volume is in milliliters, so I'm going to need to convert to liters. So we know 1,000 milliliters to 1 liter, so 12,000 milliliters would be 12 liters. And again, that makes our liters cancel out. And on the bottom we have R, which is already there, and N, the number of moles, which is what we want there. And we have 4 moles. And we're not going to worry too much about significant figures in this one, just to make sure we get our process down right. So the moles are going to cancel out there. So our only unit that's left from our constant is K, which is what we want for our temperature. So we're going to get our calculator out and figure out the answer. And let's move down here, give ourselves a little more space. And according to my calculations, we have 197 degrees Kelvin. Again, we're not going to worry too much about significant figures here. And if we subtract the 273 from that, this would correspond to negative 76 degrees Celsius. Okay, if they wanted us to record it in Celsius. Right. So you see, it's not too bad. It's actually a pretty convenient way of solving problems for us. We just need the formula again, plug in, and then the answer. So it's a nice convenient way to work with gases as long as we know 3 of the 4 variables. Again, if we have a situation where we're just changing one variable, we may have to use one of the other gas laws. But if we know 3 of the 4 variables and solving for the 4th one, the ideal gas law seems to work out very well for us.